Hello and welcome. Today I'm going to be talking about JSON denial of service attacks in Scala. So just a little bit of introduction from me. So my name is Sam Halliday, and I wrote Functional Programming for Mortals with Scala Z, which, given that this is a functional programming conference, feel free to treat yourself to a copy. They're all free. It's a completely free book. You can pay if you want, but you don't have to. You can always bring it down to zero. You can get it at this URL. And source code's available online. So a little bit of a refresher because not everyone knows all of the principles of functional programming. So we're going to be talking a little bit about type classes, but not very much. So I put type classes in quotes because Scala doesn't have type classes. It has an encoding of a type class. It's actually a concept from Haskell. So when I'm talking about decoders or encoders, this is what I mean. I mean a trait that has a type parameter on it, and decoding JSON, we get some JSON object and we return either a failure or a success. So if something has a decoder, what we mean by that is they have an implicit value somewhere in some implicit scope that provides this interface so that we can actually decode a JSON into a failure or the object itself. And we would say that this is a covariant type class because the type parameter, is on the return type. And conversely, the encoder is contravariant because the A is the input parameter and we receive a JSON whenever we do that. So encoders can't fail. So this is what I mean if I talk about a type class. And when I'm talking about encoding and decoding, this is the interface that we're really talking about. The other thing that's important for this talk are abstract data types. So these can be encoded in Scala through case classes, and they're more academically known as products, or sealed traits, which are known as coproducts or sum types, and then primitive values, things like object, integers, strings, booleans, that kind of thing, the ends of the tree. And I'm going to be talking about ASTs, so abstract syntax tree. And for JSON, what we mean there is modeling the language of JSON as an ADT, an abstract data type, so just as a data type. And here, this is a very idiomatic way of encoding JSON. In a lot of libraries, you're going to see this kind of thing where a value in JSON can be one of these many different kinds of things. The most popular one, of course, is that there's an object. It's really just a map from strings to other values. And because it's got itself in it, we say that this is recursive. It's a recursive type. Or arrays, which is just a list of values. Booleans and strings and numbers being the primitive types. And then you can also have a null, which I guess is also a primitive type. And everything can more or less appear anywhere else. So this is the JSON AST. And why am I talking about that? Because, some of you might remember back to these days. Do you remember? This was 5 years ago when I think this is Matthew raised a request on the Scala improvement process to introduce a standard JSON AST into the standard library. And I don't know about you, but I miss the days whenever the biggest drama in Scala was technical like this instead of somebody releasing another dossier on somebody on Twitter. Like I really miss those days. So I wish we would get more dramas like this where it's all technical. And this thread went on forever. It was on Reddit. It was on Hacker News. Everyone was talking about it. All my friends were asking me what's going on in Scala because of this. It's obviously a very emotional topic for everybody, these JSON ASTs and APIs. So what's it all about? So this thread went on forever. There's, Martin there setting the tone of a welcoming and inclusive community. I said some really stupid stuff on that thread. We'll come back to why it was so stupid. And it just went on forever and ever and ever. And everyone just wanted this thread to end and go away at some point, which it eventually did. But, there's a different take on it. Let's say there is no AST. What happens if there is no AST for JSON? And why would we want to think that? And my whole thesis here is, well, let's think about denial of service and how we can actually do that to a service. Now, what do I mean by denial of service? I don't mean this kind of denial of service. This is really a denial of communication. But if we take another example from the Scala ecosystem, this is the kind of denial of service I'm talking about. If anyone knows Scala Steward, it's this bot on GitHub that goes and upgrades everybody's dependencies. And it does so much work, so many commits, that if you go and try to look at its homepage on github.com, just try that in a browser right now, you'll get the unicorn of death. because there's so much there that GitHub can't even render it. And that's kind of what we mean. Although a denial of service attack is typically by an adversary, and in this case, it's more accidental. Scala Steward aren't doing this on purpose. It's just pushed GitHub to its limits. So a DOS attack, a denial of service attack, is a cyber attack where an adversary makes a resource unavailable to its intended users by disrupting services. They do that by using up resources that would otherwise be spent working to help those intended users. Now, here's the big news, and the thing that everyone should be concerned about is that JSON servers written in Scala are all vulnerable. Yeah, you should be scared about that because I've got a lot of actual exploits that we're going to look at in this talk. So what kind of attacks, what kind of things are we talking about? The first one, actually, before we go into the attack, let's pick some example JSON, right? So let's say you're talking to a service, and this is an example of the kind of JSON that they would expect you to send to them. This is Google Maps API, but it could really be anything at all. I just picked this because it's got some stuff in it that's useful. We've got an object here. It's got keys to values. There's some arrays in there. There's some primitive values. There's numbers expected. There's strings expected. We can do a whole host of different attacks with this kind of thing. So we're going to build on top of this baseline. And the point of our attack is going to be that the server needs to see exactly the same message as it would get from this, but we're going to adapt the JSON in some way such that we're going to use up a lot more resources from the server. Okay, so the first attack we can do is just whitespace, right? JSON allows whitespace anywhere. So we can just add a whole load of whitespace. If we add a gigabyte of whitespace onto the valid payload, that means that every request is now costing the server 1 gigabyte of heap. Like that communication between us and the server can be compressed. So we're not even paying for that 1 gigabyte of network usage, but the server is still loading that into memory somewhere. It's taking that, it's converting into an array of bytes. Most of that is just white space, and they're wasting their heap. Now, they might mitigate against that by doing some kind of asynchronous parsing or something like that, but most servers are actually loading that into memory. If you do a lot of these, you can just take the whole service out of memory exception. There is a very simple mitigation. Sorry, I'm hearing some background there. So the mitigation here is we just put a limit on the message size. So we can say no one's allowed to send us a message that's more than 1 megabyte. Fine. Then we can always provision our services such that no one can ever take down our service. Okay, so that's a real simple one. We're going to get more advanced than that. The next thing is redundant data. So let's find an object in that valid JSON, and let's just add a new key and a really, really big value. Or we can find some string that isn't actually used for business processing. And this happens a lot where there's just redundant fields that are just there, part of the data model. Everything will fail if you don't provide it, but it's never used for anything. A lot of the time you'll find like a debug string or something like that that you could adapt. So there's a couple of different ways you can inject this attack. So here it is. It's the same JSON string, but now we're putting in a really big redundant key and value, really big thing here. And stick some Unicode in there as well. My favorite Unicode character is the Unicode monkey. So, have that. But like, why stop at like 5 or 6 lines of text? We can put as much in as we want, but fill it up the whole 1 megabyte that we're allowed. And you'll be guaranteed that the server on the other side will have to parse this. It'll have to deal with the fact that there's Unicode in there. It'll have to allocate memory. It'll end up allocating about 2 or 3 times the amount of memory that this really takes up. And you're attacking the heap. Okay, so you're now trying to use up as much memory as possible, and also processor time to parse it as well. So we can do that as an attack. Now let's more interesting ones, hashcode collisions. So let's find another object. Let's go back into that JSON, and let's add lots of keys. So the values can all be null, but what we might want to do here is just add lots and lots of collisions, because here's an example. So the original message had destination addresses and then an array in there. This string has exactly the same hash code as destination addresses. We can put it in there. This is valid JSON. when the server receives this message, it's going to have to convert all of this into a hash map, and it's going to get a lot of hash code collisions. And we'll do that for every single key in the JSON. And I've only done one collision here for destination addresses, but of course you can fill that up. Put 1,000 of them in there, put 1,000,000 in there if you can. Why not? Fill it up as much as you can until you hit that message size limit, and you're going to make the server do work. So there's an even better attack that we can do, which is if we find hash codes, if we want to put in keys that have hash code of 0, right? It turns out that older JDKs will not cache that. So what happens inside string in the JDK is it's a bit like this. This is the pseudocode. So there's a mutable variable in there, hashcode underscore. It's set to 0 by default. And when you ask for the hash code of a string, it'll check if it's 0. And if it's 0, it'll do the work. And if it's not 0, it'll return the cache. So if your hash code actually is 0, you're going to force the JVM to do the work every single time. So if you've got a really, 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 really big string that has a hash code of 0, you can force, that server to do a lot of CPU work. Now, in more modern JVMs, and I think this is from JDK 15, it was only added last April. They added another immutable variable. So they're actually tracking if the hash code is 0, which is kind of interesting because that's a big cost. Every single string in your JVM is now going to use up another 32 or 64 bits of memory every single instance, just because the people who are releasing the JVM recognize that this is a security exploit. So, we're all now paying the cost of that exploit existing there. And of course, when the JDK releases a new version, it always has to be backwards compatible. So how is the hash code actually calculated, right? So this is again pseudocode, but it's effectively the same algorithm. So we start with some counter, let's call it H. We set it to 0, and we go through every character in the string. We multiply the old number by 31, and then we add some bitwise manipulation of our character on top of that. And we keep on going until the end. And then it'll just naturally overflow if the array is really big. But there's an exploit here. Can you see what happens if you've got a prefix of your string where the hash code is 0, right? This H is 0, then we go 31 times 0 plus 0, and we keep going 0, 0, 0, 0, 0. So a prefix of arbitrary length that has a hash code of 0 will not affect the hash code of the whole string. And that's exactly what we're doing when we exploit it back in our original message. So this JSON message here, this part here has a hash code of 0. We can generate effectively an infinite number of strings that have a hash code of 0 like this. Another very obvious string that has a hash code of 0 is just the 0 character, \0, or in JSON form \U0000. And you can just add as many of those onto the string as you want. It's kind of obvious what you're doing whenever that happens. But there's many, many ways to create a string that has a hash code of 0. Or you could just use brute force to go and try to find something that has the same hash code as what's in there, if you really wanted. So why is a hash code collision causing so much work on the server side? Well, let's look at what a hash map is. And a lot of people will remember this from their algorithms, data structures 101. Of course, the Scala implementation of Hashmap is much more advanced than this, but fundamentally it boils down to the fact that a map is a list from keys to values, or an association list. And the hack that a hash map does is it breaks that up into buckets. And each bucket, you're guaranteed that the keys are all going to share the same hash code value. So typically what happens in any kind of hash map implementation is that the number of buckets depends on the number of elements that are in the overall set. And you're going to try to keep them about the same, so that you minimize having to do more advanced checks. So this little hash code shows us what's happening here. Someone adds a key and a value. We go through, we take the hash code, we modulo it by the number of buckets. We go and check and see if it exists. If it doesn't, then we want to go and see, well, hey, we're about to add a new element. Should we grow the hash map to a larger one. And if that happens, then everything gets all of its hash codes recalculated. So what we want to do if we're doing a security exploit is we want to make sure that this is as expensive as possible and force that tree in the computation to always recompute. So what we do, that's what we do whenever we have lots of hashcode collisions and lots and lots and lots and lots of keys. So we're forcing the recalculation of those things. So if you've got lots of keys and lots of that are hashcode colliding with the fields that that are actually valid, you can also put in lots and lots and lots of strings with hashcode 0, just so that we're recalculating everything all the time. So that's a really powerful attack. And I should point out, I'm not going to show numbers in this talk because it's a very short talk. But if you look at the README of the open source project, you'll be able to see all the performance statistics versus Circe versus PlayJSON. And a few other frameworks in there. And you can see that this has definitely got an impact if you do these kinds of attacks. Right, so the next thing, numbers. So if anyone has a REPL, open it up, type this in. So this is just using JDK. So there's no Scala isms here at all. We're just creating a big decimal from a string. And this big decimal, this is going to just use the number up front is 1, so that's going to be a very, very, very small number, and then it will store this number 21474834 as an integer. So this this big decimal is stored in a very, very, very compressed memory form in your JVM, and then we're just going to ask for the integer form. So that should just throw away the double precision, right? So if you did that, you might be kicked out of the meeting because your machine's about to go and spin and it could use up all your RAM. So you might want to do Control-C before it does that. I'm sorry if I kicked you off the talk. Why did that happen? So let's talk about floating point numbers for a minute. So floating point numbers have a fixed size of bit, right? So this is your 64-bit floating point numbers, also known as double numbers. The first bit is used to tell you whether it's a plus or a minus. And it's interesting to note that floating point numbers have a plus 0 and a negative 0 as well, and that's why people talk about this. It has a lot of fundamental implications. And then the fractional part is 52 of the bits that goes up front, and then it's 2 to the not 10 to the power of, but 2 to the power of the exponent, and that's given 11 bits. And then there's some other tricks where you can get a few extra bits for the fraction in various a certain part of the space, but that's more or less the way that it works. Now, we were talking about arbitrary precision. So a big integer is stored as the sign is an integer. So not just a Boolean, because big integers store 0 as a 0 integer and then an empty array for the magnitude. So they're kind of wasting a lot of space here because that, it's really just -1, 0, or +1. And then the magnitude, which is effectively, the count of where you are. So if you've got a 32-bit number and you're storing it as a big integer, then it'll just be an array of size 1, and then that you spill over to 2 if you go to 64 bits, and then you spill over as it gets bigger and bigger and bigger. So big decimals are one of those as the fractional part, and then just an integer as the exponent. So when we typed in that string, it parsed it as fraction big integer. This is a really small number, just basically 1 byte. Or one integer, so 32 bits. And then the exponent, which is again 32 bits. So really we're just about 64 bits, give or take, for some extra pointer logic. But when we ask to convert it into a big integer, it does a bit shift, the number of the exponents. So let's calculate how much memory that's going to use, right? So the maximum array length is about 2 billion. So this can have 2 billion elements. Each entry is 32 bits. You work it out, the largest number is about 64 gigabytes. So that code in the previous slide, that was about to try to allocate 64 gigabytes of heap for your number. And if you can write some JSON that forces that to happen, yes, you can totally take down the server with one very small payload. And there are JSON libraries out there in the wild that people are using that do this. So you might want to check if you're using one of those. Now that does involve your domain model to be using big integers so that it'll parse into the AST as a big decimal, and then the deserialization logic will go from big decimal to big integer, causing that. But you want to watch out for that. and people are definitely susceptible. Staying on the topic of numbers, this one is a Circe specific attack, because Circe goes to a lot of effort to make sure that the previous attack doesn't happen. It's like checking numbers as it goes. But this one is a nice one, because if the domain model is an integer, we can force Circe to parse a very, very, very large double number just by putting .0 and thousands and thousands, but a million of these things after it. And then that'll actually eat up a lot of memory just in Circe. Play JSON, I think, is not susceptible to this one, but Circe definitely is. And it's a bit like redundant data, but it's even more stealthy, because it's really, really, really hard to see what's going on. Even if you look at the AST, you can't really see what's going on with this one. So it's very, very difficult to detect what's happening if you're attacked by this. So what can we talk? Let's talk about mitigations. So that's what I mean by no AST. If we just go straight from the wire into the domain object, which is what we do here in this little library, then there's no AST to attack. So any attacks are actually entirely domain specific. And that's exactly what I experimented with. So what do we mean by that? Well, let's say we've got a decoder of a Boolean. If on your business logic, you're expecting to see a Boolean in a specific position, then when you're decoding from the wire into that, then you'll literally just look for the character T or F, and then depending on that, you'll look for the rest of the keyword. Otherwise, you'll fail. And inside this library, we're throwing exceptions that don't have stack traces, because we've got a pure API that's exposed to the users, but then under the hood, we're using exceptions for the failure case, so that we don't ever have to pay the costs of either on the fast path, which helps with performance. So we could go through all the primitive types like this. There's a from scratch number parser and all that kind of stuff that reads one character at a time. But I won't go through that. There's a very short talk, so if you want to see the details again, look at the source code for that. So what about from a user perspective? How does that work? Do you have to write really long pieces of boilerplate? Well, no, because we can use Magnolia macros to generate all this code for you. So as a user of that library, you would type just a case class, and then you would just call some Magnolia macros here. Now you've got an encoder and a decoder for this thing. If you're using Scala Z deriving, you don't even need to type that. You can just do @deriving and then type in the name of the decoder and the encoder. And then in your REPL, you would be able to type stuff like this. So, you produce JSON out of it, or you parse the JSON. But this is not going through an intermediate form. It's going straight from the wire into your object type. And when we're encoding, we're going straight from the domain object straight to the wire. So there's, we get a huge performance boost from that as well, because we're not copying the arrays all the time. We're just going straight from whatever's there into whatever it is that you expect, nothing in between. And that gives us a huge performance boost as well. So let's talk about some of the other things that we're doing there. So string values are not materialized by default. That means if there's some, some string like redundant data attack in the JSON, we'll just parse it right to the end, and it won't use up any memory at all, right? So it's just not materialized. But what we also do is, if that's legitimate and it's not an attack, it can still be a performance bottleneck, because a lot of the time people put things like CSV or base64 inside a string inside their JSON, and that means you've got the string gets materialized, and then that gets turned into another reader that then gets passed on to something else. We just expose it straight through, and there's no memory allocation whatsoever. Every single character at a time is passed through to the nested decoder. Object keys, we don't even materialize the strings of object keys. We've got a fast bit set that keeps track of matches. It's basically a super optimized state machine that means we're not using regular expressions or anything. It's really just optimized to looking for string matches, and that can be orders of magnitude faster, and zero memory allocation as well. We have, because JSON is supposed to be arbitrary, you're supposed to allow people to add keys that aren't expected there. We leave that open so that we allow extra keys to be added. but we have an annotation that you can add which says, if someone gives me a key on an object that I didn't expect, then fail immediately. So then if you've got a really strict schema that you're expecting people to code to, you can just reject that any kind of attack vector like that whatsoever straight away as an instant failure. And numbers are never materialized, so we're saving some space there, especially the death by 1,000 zeros attack. We're now not even loading that into a string, and all the other frameworks do, even if they're not susceptible to an actual CPU attack. They're still susceptible to a memory attack. Whereas with this parser, there's zero memory cost whatsoever to that. And the from scratch number parser is actually faster than the standard library one, which is interesting. So it can be reused for other things like that. And compile times are really fast as well. So it's not just about runtime performance. Because we're using Magnolia, like no shapeless, basically. It means we get really fast compile times. There's even a bug report on the issue tracker that says compile times of the tests are too slow because we're using Circe and Play to compare that our results, that the output is identical, but the compile times of those other frameworks in the tests is actually slowing down the entire build, which I find to be very funny. And once Java Loom arrives in a couple of years, we can avoid even more heap allocations because we've written this on top of Java Reader. And we should, like, I wouldn't be naive enough to expect that the Java Reader that comes out of the box is going to be, async and all that. But I would expect that we would be able to write some kind of interface over NIO that looks synchronous, but actually under the hood is using Loom. And not blocking any threads. Now, it might not be the fastest thing in the world in terms of latency, but whenever you're serving 10,000 requests a second or 20,000 requests a second, you care about throughput. And in that case, imagine having zero memory overhead whatsoever for everything that's coming in off the wire. You're really just paying for your domain model at that point, and we're completely prepared for that. So this is all open source, but I'd written this, I'd called it JSON. And the thing is, writing an open source library for Scala these days incurs a lot of other things, like you need to find maintainers who are going to package and release for Scala.js, Scala native. You have to cross-build for 4 different versions of Scala. You have to rewrite it for Scala 3. You have to add integrations for other frameworks, get a logo, a microsite. You didn't have to do any of this 10 years ago. 10 getter badges and agree on formatting rules, which is the hardest possible thing in any open source project, and find a welcoming and inclusive community that can go and try to get this used places. So I'm scratching my head wondering, well, I can't do all of that on my own anymore, even though it's a really small library. So who should I go and talk to? Maybe I should go and talk to the people that write the JSON libraries that everybody's using already. Oh no, it won't talk to me. But I was told that maybe if I was to write it in a tweet and then delete the tweet, he might read it then. I don't know. We'll see if that works. But then I found JSON, the ZIO JSON community, and they really ran with it. And this library is now available for everybody to use. And I hope you enjoy it. And I hope it helps you plug security holes in your programs. That's the end. I really want to thank Andrei Plokotnik, who wrote JSON under Scala. He discovered a lot of this years before I did. So he's really the inventor of this entire idea. And JSON under Scala, it's implemented as a macro. That's not the way I wanted to implement the library. I wanted to keep it simple, but all these ideas are his.